They're going to be talking about this great, very long title, which is Taming the Microservice with gRPC and Kubernetes. And it's very long, so long that doesn't fit in one line. So I changed the name, which is Building System Like a Googler, or if you prefer, Coding Like a Googler. The idea is that, so when I joined Google, I was a software engineer, and I loved it, because there was a bunch of things that I could use that were just amazing. Like for a developer, the fact that you can just write your code and you have the compiler is magic, deploying is magic, everything is magic. It's basically there's SREs behind it, but they're magic too. So you're like, yeah, everything just works. And then started doing open source, and it was not the same. I was missing a lot of stuff. So nowadays, we can already use the same tools I used to use at Google, but externally. So that's what I'm going to be talking about today. So we're going to be writing code, running code, sending messages, and there's going to be demos everywhere, and not much testing. Testing is a different talk. OK, so who am I? I'm a developer advocate. As I said, I work for the Google Cloud Platform and the Go team. You're going to see, oh, I don't. OK, you're going to see Gophers everywhere. Like, that's me. I'm also on Twitter, Facebook. No, I'm also on Facebook, but don't look for me. And also, I have an email, as a lot of people. Whoops, sorry. I also speak French, but I'm very jet-lagged, so I'm not going to speak French today, just so you know. But if you want to ask questions at the end, you can totally ask the question in French. I will understand you and reply in whatever I feel like. OK, so writing code. How do you write code when you're a Googler? I would like to say it's Go. It's not the case yet, but one day, maybe. Nowadays, Google writes code in a bunch of different languages. Actually, not that many. Mostly C++, Java, Go, Python, not that much, and a bunch of JavaScript everywhere. So that's pretty much what we do. But I'm going to be talking about Go, because I'm a Gopher. So why Go? There's this sentence that I really like, this quote. So to program is to engage in a pastime similar to banging one's head against a wall, but with fewer opportunities of reward. And this is something that, depending on what language you might have used, you might have felt. So what's about that? Well, that's simplicity. If the language is too complicated, if the whole language doesn't fit in your head, you're going to have a bad time. So the idea is, let's make it as simple as possible so you can concentrate on the problem rather than on how you solve it. This one is a really good one. Bjorn Strostrup, creator of C++, said, C makes it easy to shoot yourself in the foot. C++ makes it harder, but when you do, it blows away your whole leg, which is I really like it. And what is this about? Clearly, memory corruption. And Go is actually a safe language. It's safe in many ways. It's type safe. We don't have void star. How many of you have used Go? OK, oh, that's a lot. Good. How many of you have used C? And void star, like the void pointer. OK, we don't have those. Those are evil. We don't have those in Go. We actually have them, but we hide them very well. So you're going to use them. There's also no implicit conversion, so having things like overflows in the integers, they don't happen that often. You actually have to say, I know what I'm doing. And same for memory. We have pointers, but no pointers are arithmetic. So you're going to go, this is the address, add 4, and see what I get. There's also no memory buffer overflows. And since it's garbage collected, there's no memory leaks, unless you have them. And then that's a different thing. But it's easier to write code that doesn't have memory leaks. This one, I'm not going to read it because it's really hard to read at the end. But some people, when confronted with a problem, think, I know, I'll use threads. And they have whatever. What is this about? This is concurrency. And concurrency is very important. Nowadays, everyone uses concurrency. And some people choose, some languages choose some interesting approach. Like Node.js chooses not to have concurrency at all. Well, they have concurrency, but not parallelism. Then they remove a class of problems. Go, what it does, it offers something which is Go routines and channels, which is based on communicating sequential processes, which is really old idea. like it's older than me. It's 1978. And the fact that it's an old idea doesn't mean that it's not good. There's a couple languages that have tried to implement it before, but I think that Go is probably one of the first ones that is kind of successful with that idea. Before there was Erlang, but saying Erlang was successful might be a little bit. And Go is fast. The compilation is really fast, especially if you compare it to C++. And also, execution is very fast and keeps on getting faster. The garbage collector process are now 100 times shorter than 1 year ago. So we are working on making everything really, really fast. And Gophers are fun. And I did a very scientific study to prove that Go is fun by tweeting about looking on Twitter, Golang, so much fun. And people say Go is so much fun. So scientific. OK, let's stop talking about why Go is cool, and let's do a little demo. I'm going to build an HTTP server. Simple. Let's do that. OK. So I'm going to do main.go, package main. I have my function main. In my main function, I say, you should handle all the requests with this handler. And then you're going to listen and serve on port 80 with no options. If something goes wrong, we're done. And my handler is a function that given a response writer and a request. Just going to print hello DevFest to the output. Go build. And we have a binary. And it doesn't work, because it's port 80, of course. But I'm crazy, so sudo, easy. That's going to allow me to open it. Localhost, hello DevFest. Awesome. This is an amazing demo, I know. Cool. So actually, I have a script. That's crazy. Cool. So now next step is like, oh, yeah, I have a binary. Cool. What do I do with my binary? We are in 2016. You put it in a container. OK, so how do I put this in a container? So I'm going to do from scratch, because I like small things. I'm going to add my web server as web server. I'm going to expose port 80. And then the entry point is going to be web server. Whoop. That's it. That's the whole thing. I'm going to be using Docker machine from the cloud, because this is running through my phone, so otherwise it could be pretty bad. And I'm going to do Docker build my web server. This should work. Cool. So you're going to see that the whole thing we're sending, that's the binary. It's around 7 megs. 7 megabytes, that's the whole thing we're sending. And that's actually around the size of the image, by the way. Docker run, web server. Docker run -p 8080. And what's my IP? My IP is this. No. Wait, something bad happened. Oh, yeah. Oh, OK. Something really dumb that I do every single time, so it looks like it's part of the demo. Yeah, you cannot run Mac on Linux. That's a bad move. So OK, I want to build a Linux binary from Mac. How do I do that? Go as equals Linux. Go build. That's it. Now I'm compiling a binary that works in Docker. Takes a little bit longer, but it just ends up generating the same thing. I'm going to do Docker build. It's going to send the same binary again. My phone is working. That's good. Docker run. And we got it. Now we're running in production. OK, how awful is this? Very. Because right now, we're just running one container in production. What happens if that container goes down? Whoops. What if we want to have many containers, and we want to offer some way for our users to just access one of the IPs? No, just get this list of IPs that keep on changing, by the way, and good luck. Like, that's not a way to do it. So let's talk about that. OK, running code in production. So how do we run code in production? If we want to run code in production like a Googler, let's learn first how we do it at Google. And we're going to talk about Borg. How many of you know what Borg is? OK, not that many. Borg, for Google, for other places, different things. For Google, Borg is the thing that manages all our containers. And when I say all our containers, it's a lot of them. We launch around 2 billion containers per week. That's a lot of containers. So we manage all of them across all our data centers with one single system called Borg. The way it looks for a developer, for me, when I was a software engineer at AdWords, could be you write your amazing web service called Hello World. Then you say, this is where I want to run it, that cluster there. And to do this, first, you ask people. You're going to be like, oh, yeah, that cluster is mine. You ask someone, say, yeah, IC. IC is a cluster in some data center, and it has around like 10,000 machines. So normally, you're good. I say, this is my binary. Run this binary. These are the command line parameters, like whatever flags or anything you might need. And these are the requirements. I need 100 megs of RAM, 100 megs of disk, and 0 to 1 CPU, which is not much, but it's hello world after all, like whatever. And then I want to execute 5 of them. But this is Google, right? So we can run 10,000 of them instead. What happens next? All of this. And I'm going to add very beautiful pink arrows to make it clear. First thing, you have a binary. That binary is going to be sent to a binary repository, where we're going to store it there for later use. Then we have the config file, which is the thing we just saw. And we send that to the Borg master. The Borg master will parse that and ask and understand, make sure that, first, you're actually authorized to do that. And then if you are, it will check with the scheduler and say, hey, out of all the machines that I have, give me one machine where I can execute this replica, just one by one. And then it's going to go to the machine. It's going to say, hey, you, execute that. That hey, you is actually an instruction that is sent to what we call a Borglet. And a Borglet is a little job that runs in every single machine at Google. What it does is basically Docker full, but the Google version of it. Just give me the binary, and then starts executing it in a container. It's not a Docker container. It's a different container, but it's kind of the same idea. And soon you have 10,000 hello worlds going around a data center. They really look like this. The data centers, not the hello worlds. And to run like 10,000 of them might take like 2.5 minutes, which might feel like it's a lot, but it's 10,000 jobs. So it's kind of decent. And it's actually taking longer, because we're stopping from time to time to make sure that other containers will also have the chance to be scheduled. So we don't just get 10,000 at a time executed. We do 100, we wait, do 100, we wait, and so on. By the way, this little line here never gets to 10,000. Because when you get to 10,000, the probability of one of your jobs being removed from production or just failing is high enough that you will get to like 9,998, something like that, and you're happy with that. And it's totally normal. It's how life is. Machines fail all the time. OK, let's talk about Kubernetes. What is Kubernetes? To start with, how many of you know what Kubernetes is, or have heard Kubernetes, or I hear French people saying Kubernetes? OK, so Kubernetes is a container orchestrator. So it's like Borg, but for the open source community. It's not an open source version of Borg. It's actually an improvement on Borg that has some changes. One of the improvements, if you ask me, is that it's written in Go, but that's really personal. Basically, what it allows you is it allows you to run containers in a bunch of machines. Those machines could be anywhere. Could be part of the cloud, Google Cloud Platform, or Amazon, or Azure, or it could be one of your machines on your desktop, or even could be, if some of you have seen, a bunch of Raspberry Pis. We've done that. We've executed Kubernetes on a cluster of 4 Raspberry Pis, which is fun because then you can unplug them and stuff like that. And it's really fun. If you do that at Google, they don't really let you do that. So it's an open source project with a huge open source community. I updated this a minute ago. So it's like over 24,000 commits. And not even half of them are done by Googlers. And 12,000 GitHub stars, which I guess that means it's a high project. We have a lot of partners. It's not Google by itself. We have very important partners like CoreOS, but also Microsoft with Azure and IBM and so on. So basically, it's a bunch of cloud people getting together and trying to do something fun. So how does this work? Well, this looks really similar. So you got your config file, and you have your container image, Docker image, or Rocket image, or AppC image. Let's go with Docker. You send that Docker image to a Docker repo, a Docker repository, or Docker hub. Then you send your config file to the Kubernetes master. Kubernetes master will talk with one of the schedulers. This is something that you can change. We have a scheduler by default, but you can change whatever. You can have whatever scheduler you want to have. And then it will send it to one of the machines in the cluster and say, hey, kubelet, execute this image. Kubelet will go fetch it from the repository and start executing it. That's it. OK, let's create a Kubernetes cluster. So this is actually Container Engine. Container Engine is a managed version of Kubernetes. So Paris DevFest. Going to say, I want these machines. I want 3 of them. And I want all the things working. And that takes like 2 to 3 minutes. So let's see what this is doing. OK, what is Kubernetes? Kubernetes, there's basically 3 or 4 concepts, and with that, you get the whole thing. First, we have pods. And pods are groups of containers. Very often, 1, but sometimes more. Why do we have pods? Because if you have some containers that are supposed to live and die together, it makes sense that they are together all the time. One instance of this could be you have an application, and then you have a log collector. If the application dies, once the log collector is there, but the application is dead, what is it doing there? Nothing. Should just get removed completely. That happens all the time, right? So we have a pod. Pods are pretty cool because they have unique IPs. So now it's not your hosts or your machines that have IPs, it's your pods. And if you have 100 pods in one machine, every single pod has a different IP. Why is this important? Because it means they can communicate very easily. Regardless of where they are, they have the same IP regardless of the machine where they're being executed, which is pretty good. But even better, you don't need to fight for who owns port 80. Every single pod has port 80 by itself. So that's pretty cool. Then we have labels. And labels are just that. You label stuff. That's it. Done. And this sounds really simple, but it's actually super powerful. This is one of the things that Borg doesn't have, and we added because we realized that it was really powerful and we needed it. So what you do is you say, I'm going to use labels to say, this pod is a front end, and it's version 2 of the front end, by the way. And then we can have things like replica controller. And a replica controller, you will say, I want 2 of these things. And the way you say these things is by saying the labels. I want 2 front ends of version 2. Then you can say, now I want 1, it will modify it. Now, the important thing is that you don't say start 1 or stop 1. You say, I want 2. And why is this important? Well, let's imagine that we have 4 nodes and 4 pods. And by chance, we have 1 pod per machine. And somehow, catastrophe strikes, and one of the machines is gone. Now we said we wanted 4 pods, And the Kubernetes master sees that there's only 3 running. So what does it do? Starts a new one. You don't have to do anything, because you didn't say start 4. You say, I want 4. So a new one will be started in some node. That's it. Quite simple. And finally, we have services. And services are used to be able to solve that problem of you have a bunch of pods, they keep on dying and reappearing and moving around. What IP do I give to my clients? Well, you give the IP of the service. So that service, what it will do load balancing across a bunch of pods. And the way it targets those pods is via labels. So we'll say, I'm targeting all the front ends v2. So if you have one extra front end of v1, so if you have one extra front end that is v2, that service is not sending messages to that one. But then you can remove one of the labels, and they just all the front ends, and that could work too. So it's very flexible, and you can do whatever you want. We'll see that in a minute. OK, let's deploy our amazing server. Yay, it's up. First thing I'm going to do is I'm going to do cluster, what's the name? Paris DevFest. So this, you do it only once. And it's basically saying, I'm going to be using this cluster. So the kubectl, which is the kube controller tool, will be managing that cluster. You might have more than one, so it's important to say it. Oh, yeah, that's, well, it's going to be a little bit slower. OK. Zone. OK. Clusters. Cool. Cool. OK. Now I can do kubectl get pods. And it's going to say there's no pods, which makes sense, because there's no pods yet. But I can also do, I have an alias, so now I'm going to start just typing k, because it's quite shorter. Get nodes. It's going to tell you there's actually 3 nodes. They're all running, and they've been running for the last 3 minutes. And you can have labels on those, too, so you can do pretty cool stuff. Cool. So how do I run my web server on that cluster? What I'm going to do is I'm going to have a web server.yaml. And this looks like a lot of code, but it's just because I have some things. Oh, by the way, I need. That's magic. Don't pay attention to it yet. I have a visualizer, and for the visualizer, I add metadata to everything that I generate to say, I want to visualize that. You don't need that in general. The important things here are, this is a replica controller. And what I'm saying is the name of the replica controller is web server v1. I have 1 replica. And what I want to do is the selector is things that are named web server version 1. That's what I want to run. And then when you need more, this is the template. So that's a pod. It's the metadata, it's labels, name, web server, version 1, and also I want to visualize it. And the specs, that's an interesting part. It's web server, and then we have that image there, gcr.io/DevFest Paris 2016 web server. What is gcr.io? Does anyone know what GCR is? 1 person. 2. OK, GCR is Google Container Registry. And this is very useful, because if you're putting things on Docker Hub, by default, they're public, meaning that I can go and pull them and find your code. Yay. That's not really cool. So we offer Docker Container Registry that is associated to your own project. And no one else that your own machines are able to access it. So it's pretty safe. OK, so we're going to need to put our image up there. So I'm going to tag my web server as that thing, version, no version, Docker tag. Wow. Docker tag web server. Cool. Docker tag -f. I'm really not good at this today. Docker tag. Docker tag. OK, I'm going to make it a little bit smaller. Web server. I'm going to tag it, and now Docker push this. And this is going to fail, saying, wait, Docker, we don't know what GCR is. Might take a long time, but it will fail. So you just say, gcloud, do this. And we'll just push it. Now we're doing that first step of sending that container to the Docker registry. There is a Docker registry that's only for us. Everything worked. Cool. Now I'm going to do create. I'm going to say, create that web server.yaml. This is my try. I was like, create that replica controller. Gonna create it. Cool. Get pods. There's one pod, is starting. Get replica controllers. There's one replica controller that is there. We have selectors and everything. Also, not that one. No, that one. Localhost, this one. No. OK, 1 second. That's supposed to work. OK. Well, that's going to be painful. OK, so we have one replica controller, the blue one pod, the white one. Cool. Now, what if I want to have more of those? I can come here and be scale the replica controller web server v1 to have replicas, I don't know, 10. It won't fit. But now you have 10 replica controllers. Boom, done. Let's make it a little bit less than that. Let's make it only 5. Oosh, no, 5. OK, let's make it only 5 so it actually fits in the screen. And now let's choose one of the ones that survived. Get pods. And be really evil and just delete it. So what happens if I delete this? Now I have 5 and back to 6, which that's not what I said. I said 5. So now one disappears. What happened? Actually, I said delete this pod, but the pod was shutting down. Well, it was shutting down. We knew it was still there, but it was shutting down. So we started a new one before that one died. And now it's dead. We remove it. What happens if you lose a machine? Exactly the same. You don't need to care about that, which is pretty cool. Now, how do you access that? Well, you could do something like, I'm going to start a curl pod. Curl pod is just something that allows me to do curl. It's just a pod. And now, so you have to get pods. You see there's the curl pod. I can do exec -it curl pod sh. I'm connecting as an SSH into that pod. And now I can do curl to whatever I want. So I can be here and say, give me the pods again. We're going to get this one, describe that pod. That's a lot of information. Just give me the IP. I really have issues using this. OK, that's the IP. I can come here, curl that one, hello DevFest. My web server is working. But that's an internal IP, right? And that's only one of the pods. How do I give access to all the pods all the time, regardless of them dying? That's what we call a service. So our service, everything it says is we're going to create a new service. We're going to call it web server. It opens the port 80. We're naming it HTTP. And then we're creating the type is load balancer. And when we say type is load balancer, something really cool happens. On Container Engine, it will create an actual load balancer with a public IP. So everything inside is private, but you now have access to those. So create, no, that one. Create service. Service is created. And now we have that server there. Now, you make it a little bit bigger. You will see that there's an IP there. That IP is private right now. But what's going on is Google Container Engine uses an API call to Google Cloud Platform to say, create a new load balancer and give me the IP. So in a minute or so, this should work. In the meanwhile, we can actually use this IP from our amazing curl pod. So we can curl there. And it keeps on working. And every single time is a different pod that replies. How do we know that? You trust me, because I'm a Googler. No, that's not good enough. So instead, what we're going to do now is, I want my web server to also tell me which web server it is. So what we're going to do is we're going to go here, modify the code, and I'm going to add, at the end, get the environment variable, hostname. Now, go as Linux, go build. In the meanwhile, here, you can see that we got the public IP. So that works. That's pretty cool. And Docker build. Actually, Docker build, Docker push, all of those things. I already did it before, so you don't need to see it now. So instead, what I'm going to do is I'm going to deploy. I'm going to move. We have the version 1 and the version 2. I'm going to create a new replica controller. And that new replica controller is actually pretty similar to the first one. The only difference is the name is v2. It uses version 2 as labels, and version 2 for the Docker image. That's the only thing. Now I could create it. If I created this, I could end up with 5 pods of version 1, 5 pods of version 2, and that service serving to all of those. That's not really what I want. What I want is to replace those 5 that I have with 5 new ones. So I can do that. And to do that is actually pretty awesome. Rolling update. Update period is 2 seconds. The service is called web server v1, and I want to move it to v2. And now what it's doing, it's saying, I'm going to create a new replica controller. And I'm going to start a new pod of version 2. You cannot really see it, but there's that 2 right there. Once I see this one is running, I'm going to stop one of version 1. Then I'm going to do a new one, version 2. So you can see it here. Actually, let me see if I can put both together. That might be a little bit too much. No, might work. No, OK. OK, so we got the version v2 to v2. We're going to take the v1 to v3, and so on. We're going to keep on moving. Now, the cool thing is that if in the meanwhile, we have something like while do curl that sleep 1 done. You're going to see that we're going to get something. Did I break something? Wow. While do curl http that URL sleep 1 done. While is broken. OK. Maybe curl is broken. Let's see. Curl. I think that my Wi-Fi stopped working. Oh, that's why. OK. Let me use my personal Wi-Fi. That might work a little bit better. I don't know how that's working, because it doesn't have access to it. So, connection refused. Everything is down. Cloud demos without Wi-Fi, quite hard. Nope, everything is down. Wait, this is working. Yeah, OK. So why is this work? Am I using the wrong one? Oh, yeah, I'm totally using the wrong one. OK, so that's why. Might be too late for that. OK, you're seeing the new version already. OK, you could have seen that it was moving from version 1. Oh, there you go. We still have some of the pods are version 1. So we're going to keep on seeing hello DevFest by itself. But otherwise, you're going to see that we actually get the pod ID, and it keeps on changing all the time. So we're actually doing load balancing across all the versions. As soon as we get to 0, which could be quite soon, we took it down to 4, 2. It's going to take a little bit more, because the Wi-Fi is really slow, so it takes some time to manage it. But as soon as it's done, what it's going to do is going to remove the replica controller for web server v1, and then we're done. If we wanted to back up, everything you need to do is to do exactly the same thing, but backwards. Web server v2, and the file could be for version 1. So you're moving from v2 to v1. That's it. That's everything you need to do. I think this is pretty cool. If I was supposed to deliver, like deploy stuff, these kind of things is what I expect. Cool. Let me see. We're kind of short on time. OK. So communicating across containers. We now have Go binaries running in production. They're running all the time. If something goes down, just start up again. If a machine goes down, start up again. Nothing bad happens. We're all happy. Except that we need to communicate between messages. And there's different ways of doing it. One of the ways that a lot of people are using is REST. Just use REST APIs everywhere. And REST APIs are very good for public APIs. But I could say that if you have something that needs to be very performant, REST is not the best option. Because it's actually, it has a lot of things that you're actually not using. HTTP is a pretty complex protocol. So using just HTTP for that is kind of hard. On top of that, you need to adapt your API to be a get, a post, a put, or a delete. If it's something that doesn't match that, well, you have to choose one. So it's kind of weird. At Google, we don't use that. At Google, we use Stubby, and Stubby, open sourced, is gRPC. The best part is, who knows what gRPC stands for? Exactly. I thought it was Google Remote Procedure Call, but no, it's gRPC Remote Procedure Call, because it's a fractal, which is amazing. That blew my mind. OK, so what is gRPC? gRPC, basically, the main idea is we want something that will be efficient and easy to use. It needs to be idiomatic, meaning that you don't need to end up writing really weird code to build a server or a client for this. It needs to be performant and scalable, which means that it needs to handle things like throttling, if a server goes down, be able to send it somewhere else, load balancing, but also needs to be performant, so it should send as little bits as possible. The amount of data we send over the wire will be much smaller than what we would send with REST. And finally, microservices need this. If you're doing microservices over REST, there's going to be a bunch of things that are going to be really hard to manage, especially versioning. That's one of those that can be pretty hard. There's ways of doing it, but can be pretty complex. So what is gRPC? It's an IDL, intermediate design language, or domain language. I'm actually not completely sure about that one, where you describe your API. If you've used Swagger, gRPC is like a very, 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 very boiled down and simple version of Swagger. You describe your API in a very simple way. That's it. And then it generates things for you. It generates code for the server and the client. For the server, we don't really care that much, because you write a server once. But for the client, that's pretty cool. Because when you're writing the client, you're going to be able to generate code for Python, for Java, for Objective-C, whatever. Also, it supports point-to-point. So, hey, get, request. But also, it supports streaming and bidirectional streaming. So you can have a communication between two servers that keep on sharing data with each other, which is something that tends to be quite hard unless you're doing it by yourself. So the way it works, we have servers, we have clients. Servers implement some interface, and the clients use some stubs, which is basically like a auto-generated library that they can use to do the calls. So to get started, you just write a profile, you compile it, generate code, fill the gaps. Easy. And that's what we're going to do. Language support. We have 3 native languages. We have C, Go, Java. All the rest are bindings for C. So if you want to use JavaScript, it will be a binding on C, which means that it works very well on Node.js, not on Chrome yet. We're working on that. The way it works is you send a message, you receive a response, except that on top of that, there's not only binary blobs, there's also metadata. And this is what helps you manage versions. Not only you're sending, hey, like 42. You're actually saying, this is this message with that ID, version I don't know what, and that field has the value 42. So it's slightly more expensive than sending a blob, but it scales much better. If you have a stream, you send the metadata once, and then all the blobs, which is pretty efficient. I said that gRPC works on HTTP2. I mean, there's been talks about HTTP2. So how many of you know why HTTP2 is cool? Not that many people. OK, I have HTTP2 is awesome, and I don't have time. So I'm just going to show this demo, especially with crappy Wi-Fi. This is going to be awesome. OK, this is HTTP 1.0. We have 6 connections downloading tiles, and you can see how they're falling one by one. Actually, 6 by 6, because that's what Chrome does. I think it's 6. I'm not sure. With HTTP2, we send all the requests. We get all the responses. That's why HTTP2 is cool. And now you can do that for your messages. So what we're doing is sending protocol buffers over HTTP2. We know why HTTP2 is cool. What is protocol buffers? Protocol buffers are a way of encoding data. That's it. Quite simple. It's like encoding data in blobs, in binary blobs, but with metadata and a language surrounding it that helps you understand what you actually encoded. It's what we use at Google for everything. We have, like probably over 50,000 different definitions of messages. Everything at Google is protocol buffers. We store things as protocol buffers. We send things over the wire as protocol buffers. If it needs to be encoded, it is a protocol buffer, basically. And the good thing about it is that you can use it for many things, and it supports versioning very well. So you can have something that you're storing that binary in a data store, and then 1 year later, you're still able to read it because you have different versions, but they're still compatible. Why protocol buffers? They're compact. Versioning generates idiomatic code, so you're going to see how to use it in Go. Very simple. And they're strongly typed. I'm a static typed person. I like compiler errors. Protocol buffer will give you compiler errors, which is awesome. OK, we're not going to see this. We're just going to continue. Last demo. And I have 0 minutes to do it, so it's going to be quick. OK, so what we're going to do is we're going to open this. OK, I have my pro message. It's say. My service is called say, and you tell me what to say, and I say it back to you. Simple. The request has text, and result is sound, which is pretty cool. So what I'm going to do here, I'm going to change to my local VM, and I'm going to say gRPC go. I'm going to do proto-C, so that's the compiler. Go out. I just realized that. gRPC, say the proto, and that generated some Go. You could do the same thing with proto-C, Java out equals this, say the proto. I could generate some Java. So compiler is quite easy to use. So go doc. Generate 2 main types, request and result, and then a bunch of other types. So we have new say client, so that will generate a stub for the client, and say client. So let's see, go doc say client. It generates an interface that has a method say, which is exactly what you expect. This is the method you will call. And we have something similar for say server. This is the one we have to satisfy on the server side. So you need to do that, satisfy one and the other, and that's pretty much it. When this compile, I can go to my say server. To my server. Main.go. So main.go, I'm going to go very fast around this. But basically, you open a connection saying, I'm going to be listening on port 36060, which is what we use for RPC. You could use whatever else you wanted, by the way. And then I create a server. I register my say server, which is this thing, which is a server, which is a type on which I define that method, say. That's the whole thing I need to do. And then say, that's where the magic happens. I call random stuff. I'm going to deploy it. create server.yaml, create service.yaml, and now we're going to see if it's running. Is it running? Yeah, service, server. And now I can go to my client. I'm not going to show the code because I don't have time. Go build. Oh, I need to wait for the public URL to be able to test it. Oh, that's sad. But I generate a Go client. You could generate a JavaScript client. You could generate a Python client. It's quite easy to do, really. Get services. No. No. This demo is cool. I stayed till 3 a.m. yesterday to make it work. I'm going to wait for this. OK, client, backend equals this, 36060. Hello, DevFest Paris. And knowing how this works, time at 5 seconds. OK.
Hello, DevFest Paris.
Awesome. So what I end up doing is generating this thing that could not run on App Engine, because I'm calling text-to-wave, which is a Ubuntu package that I installed. So to do that, I end up running it somewhere. The easiest place to run it, whoop, I have a meeting. The easiest place to run it is, of course, on Container Engine. If that server died for some reason, I don't care. It will restart anyway. So these are all the things we've been talking about today. There's a bunch of things that you might want to learn. If you're interested about Go on gRPC specifically, there's a very good talk by Samir Ashmani from the Go team. And he talks about how to do bidirectional and cancellation and all of these things that you actually want to do when you're doing real things in production. With 45 minutes, you don't have time to do real things in production. I will share at least these slides. For the rest, I might have to wait, but don't worry. How to get those slides? Find me on Twitter, send me an email, or ask me a question. Thank you.